this section, we are going to be looking at trapezoidal approximation. So one of the things that we talked about whenever we were doing Riemann sums at the beginning is we said that a trapezoid underneath the curve would work better than a rectangle to approximate that area. So our first example here asks us to find the area under the curve y equals x squared on the interval from 0 to 3 using 6 trapezoids. So in this case, if we want to graph y equals x squared, 0 squared is 0, 1 squared is 1, 2 squared is 4, and 3 squared is 9. So here is our graph of y equals x squared. And we will need to make 6 trapezoids. So that means I need to put the little halfway point for all of these. And if I draw in the trapezoids that I would have, I'm going to go ahead and make some little dots right here that are approximately at those points. And so if I draw in those trapezoids, this first one actually wouldn't even be a trapezoid. It would technically be a triangle. The next one would look like this. The next one would look like this. Here we would have our 4th trapezoid, our 5th trapezoid. Oops, a little too far over, but it'll be good enough. And our 6th trapezoid. So we have all of these trapezoids, and we need to find the area of each one. Now up here I have the area of a trapezoid. We will need this. It's 1/2 the height times base 1 plus base 2. Now the trapezoid, base 1 and base 2, these are your parallel sides. So when we're looking at each trapezoid here, those parallel sides are actually our vertical sides, which makes the height this horizontal piece here. It's kind of like what we've been thinking of as our width of our rectangle. So we need to find the area of each trapezoid. First, we've got to know the height of each one of these bars. A lot of them we already know. I know that 1 squared is 1, so I know this side right here has a height of 1. 2 squared is 4, so I know this is 4. And 3 squared is 9, so I know the length of this side right here is 9. I need to find the height of all of these intermediate points here. So this point right here, the x value is 1/2, so if we do 1/2 squared, then I know the height of this bar right here is just 1/4. This is 1.5 or 3/2, so 3/2 squared would be 9/4. That's the height of this bar right here. This point right here would be 2.5 or 5/2. 5/2 squared is going to give us 25 over 4. So if we find the area of each trapezoid, we'll have 1/2. I'm going to do this like this. I'm going to do each trapezoid, so we'll have 1/2 times the height, which for all of these, our height is 1/2. Because that is this little piece I have marked here in green, that's the width of each bar. So we've got 1/2 times 1/2 times base 1 plus base 2. So for this first trapezoid that we have here, it's a little bit odd because it's actually not a trapezoid, it's a triangle. So it would be 0 plus 1/4. So that's going to give us 1/4 times 1/4 to give us 1/16. For the second, that is this trapezoid. For the second trapezoid here, we are going to do 1/2 times 1/2, and then we will do 1/4 plus 1, which will give me 1/4 times 5/4. So I'll get 5/16. So that is our second trapezoid. Our third trapezoid, we will have 1/2 times 1/2, and the bases here are 1 and 9/4. So 1 plus 9/4 is going to give us 13/4. 1/4 times 13/4 is going to give us 13 over 16. That is the area of this third trapezoid here. For the fourth trapezoid, I'm going to have 1/2 times 1/2 times 9/4 plus 4. And so that's going to give me 1/4 times, let's see, 4 would be 16 over 4, so 16 plus 9 is going to give us 25 over 16. I'm sorry, 25 over 4. Sorry about that. I'm ahead of myself. 25 over 4, which will give me 25 over 16. That is our fourth trapezoid that we have here. The next would be 1/2 times 1/2 times 4 plus 25 over 4. And so this is going to be 1/4 times, let's see, 4 would be 16 over 4, and then 16 and 25 is going to give us 41 over 4, which gives us 41 over 16. That is the fifth trapezoid, and then finally our last trapezoid. Let's see, hold on, let me highlight that one. Then our last trapezoid that we have here is going to be 1/2 times 1/2 times 25 over 4 plus 9, which is going to be 1/4 times, see, 9 times 4 is going to give you 36, plus the 25 is going to give you 61 over 4, so we get 61 over 16 here. So that is the area of our final trapezoid. To find the combined area for all of these, we want to add these together. So if we take and add all of these together, we've got 1 plus 5 plus 13. That's going to give us 19. We add 25. That's going to give us 44. Add 41. It's going to give us 85. Add 61. It's going to give us 146. So we get 146 over 16. We could simplify that into 73 over 8. And I think that's as far as that will simplify. So 73 over 8 would be the area under this curve as approximated with trapezoids. Now this process takes a pretty long time to do, so there is sort of a shortcut rule that we can use for the trapezoidal rule. And that rule is this: b minus a over 2n times f of x sub 0 plus 2f of x sub 1 plus 2f of x sub 2 all the way until you get to f of x sub n. Let's talk about what this means. Let's go back to the last problem. On the last problem, when I was adding all these together, all of them had a 1/2. That 1/2 came from the formula for the area of a trapezoid. So that area of the trapezoid was built in there, that 1/2. So I could have, if I wanted to, sort of pulled that 1/2 out front and dealt with it at the end. All of these also had this 1/2. This 1/2 is there because the height of each trapezoid, or what looks more like the width of each trapezoid here, is 1/2. I take 3 and I divide it by 6 subintervals. If you look at the trapezoidal rule, here we see b minus a over n. b minus a over n, this part right here, that is the width of each trapezoid that you're dealing with, or technically height when we're doing trapezoid, but it looks like the width on the graph. This 2 right here comes from that 1/2 that is built into the formula. Then you see that our first number we have just 1 of, but all these middle numbers we've got 2 of, and then the last one we only have 1. So if you look here, f of 0 was 0. I only used that once. F of 1/2 was 1/4. That showed up here and here. F of 1 was 1. That showed up here and here. 9/4 is in 2 places. 4 is in 2 places. 25 is over 4 is in 2 places. But 3 squared is 9, and 9 only shows up 1 time. So the first point is only going to be used once, and the last point is only going to be used once, but all of the middle points are used in 2 places. So let's look at how we can use this formula to help us do these problems just a little bit faster. So example 2 says to approximate the area under the curve y equals sine of x on the interval from 0 to pi, using the trapezoidal rule with 4 sub-intervals. So if we have 4 sub-intervals, we are going to draw these trapezoids here, and actually 2 of them are actually going to be triangles instead of trapezoids, but that's okay. We'll count them. Alright, so we could go through and find the area of each trapezoid separately, but for this I'm looking on the interval from 0 to pi. So the trapezoidal formula tells me that I would have to have 1/2 times the height, or in this case really the width of each trapezoid, which each one of these little pieces is going to be pi divided by 4. We just take the length of the full interval from 0 to pi and divide it by how many rectangles or trapezoids we have, which is 4 here. So I've got 1/2 times pi over 4. Those would be the same for every single trapezoid, so I can leave those out front. Then I can think of doing the trapezoidal formula. Well, the only thing left in that formula, 1/2 height, b1 plus b2, is this b1 plus b2. So what I'm going to do there is I would have the y coordinates for all of these, and the first one, which would be sine of 0, is only going to be there once. But I will have sine of pi over 4 twice. I'll have sine of 2 pi over 4, or just pi over 2, twice. I'll have sine of 3 pi over 4 twice. And then my last one is only going to show up there once. So I'm going to go ahead and put this together and make this pi over 8. Sine of 0 is 0. Sine of pi over 4 is the square root of 2 over 2. Sine of 2 pi over 4, which is just really pi over 2, is 1. Sine of 3 pi over 4 is the square root of 2 over 2. And sine of pi is 0. So now I can simplify these. Pi over 8 times the 2's will cancel here, and I will just have the square root of 2 plus 2. Again, these 2's will cancel, and I will just get the square root of 2. I can combine those square roots of 2, so I'll have pi over 8, and I'll have 2 square root of 2 plus 2 here. The answer might be left like this. If it's for response, definitely just leave it. You really could leave it right here if you wanted. If it's not, they may do this. They may factor the 2 out there, so you would have 2 pi times square root of 2 plus 1 all over 8, and then that 2 and 8 can reduce, so you would get pi times square root of 2 plus 1 all over 4. So this would be your approximation for that problem. If you type that into your calculator, you're going to get an estimate of about 1.896 for the answer there. Let's try the next one. We've got example 3. We're going to use the trapezoidal rule with 6 subintervals to estimate the area under the curve y equals 10 minus x squared on the interval from 2 to 3. So the trapezoidal equation just tells me I've got to have 1/2. The length of this interval is just 1, and I need 6 sub-intervals. So that means that the width, or technically height, of each trapezoid is 1/6. So that's going to go here. 1/2 and 1/6 is going to be the same for every trapezoid. Then, what I'm going to do is I'm going to take y equals 10 minus x squared, and I need to plug in each interval. Now here, this might be a little bit tougher, so I need to think about what my intervals will look like. My intervals will be from 2 to 2 and 1/6, from 2 and 1/6 to 2 and 2/6, from 2 and 2/6 to 2 and 3/6, from 2 and 3/6 to 2 and 4/6, from 2 and 4/6 to 2 and 5/6, from 2 and 5/6 to 3. So for each of these, I'm going to plug that number into this equation. So I'll have 10 minus 2 squared plus 2 times 10 minus, let's see, I guess we really should probably use fractions, or I guess we could do decimals here. Let's do decimals because we're going to type this into the calculator anyway. So 1/6 is 0.16 repeating. We'll have 2 times 10 minus 2.3 repeating squared, plus 2 times 10 minus 2.46 repeating squared. I'm going to go to the next line, plus 2 times 10 minus 2.6 repeating squared, plus, hold on, I've got this one right here wrong. This should be 2.5 right here, because 2 and 3/6 is 2.5. I was not thinking of that correctly. Then we have 2 times 10 minus 2.83 repeating squared, plus the very last one, that 3 is only going to count once, so 10 minus 3 squared. And so we would type all of this into the calculator. I'm not going to take the time to go through and do that for all of these right now. For this, I believe, if I've not made a mistake, this you should get about 10.602 for that answer. Alright, our last one we're going to look at is going to be a problem that we're going to do from a table. So in this case, they don't give us the function, they just give us the table, and you can notice by our x values here that the width of each trapezoid is not going to be the same. So if you get a problem like this, you are basically going to need to find the area of each trapezoid. So I have put a graph here to help us visualize this. Sometimes you may have numbers that may be hard to graph, so you can do it without the graph. But I'm going to draw in the trapezoids that we will be dealing with here, if my computer will cooperate. So we'll draw in each trapezoid that we will have here. This is optional. You can try to do this just from the table, but I think that especially the first time you do one of these, this helps to have this actually drawn. So if we look at that first trapezoid, each one has to be done separately here because they all have a different height. So the trapezoid formula tells us I have to have 1/2 times the height, which actually looks like width here. That is 2. Times base 1 plus base 2. So that would be 5 here and 4. So 5 plus 4. Notice if you're trying to do this from just the table, 0 to 2, that has a difference of 2, and then you've got 5 and 4 are your bases. This is the first trapezoid, so you're going to get 9 for that one. The next trapezoid, you'll have 1/2. The width of this trapezoid, or the height, I guess I should say here, is 3. I can tell that from the table because from 2 to 5, that value would be 3. So I've got 3. The height of the first base there is 4. The height of the second one is 2, which I can see in the table. I've got 4 and 2 here. So whenever I do that, I'm going to get 3/2 times 6, and that is going to be 9 as well. The next trapezoid only has a height of 1, so I'll have 1/2 times 1. My bases here have heights of 2 and 3. So for this one, I'm going to get 5/2, or 2.5. We'll see at the end which one we'd rather use here. Here you can see from 5 to 6, that's a width of 1, and then 2 and 3 are the two bases that you use. The next trapezoid has a width, or height, I guess I should say, of 3. The bases have a length of 3 and a length of 5. So that's going to give us 3/2 times 8, and that will give us 12. And then the last one, we have a height of 1, and our bases have lengths of 5 and 9. So that's going to give us 1/2 times 14, which will be 7. We can add all of these together here. So 9 and 9 is going to give us 18. This will give us 19. If we put that together, we will have 37. Then add our 2.5 to get 39.5. So your trapezoidal approximation in this case is 39.5.